In today's class, I wanted to cover some of the organization of the class and the administration of the class. And then I'm going to go on and talk about the first content of the class, which is about dimensions of nature and units of different quantities. So that's what we'll try and get through today. So just to start here, so in Physics 211, we're going to focus on understanding the motion of objects through time and space, and we're going to focus on understanding the properties of matter. And so those are the two basic contents. Just so you know, my name's Tim Gorringe. And I'll be teaching your lectures, and you'll hear from the recitation instructors and the lab instructors in your first recitation and lab classes. Here's some contact information for me. So the best email for me is this one here. It's Gorringe, my last name, and it's at pa.uky.edu. And there's office hours I posted, so the Zoom office hours I posted are on Tuesdays in the afternoon at 2:30 and on Wednesdays in the afternoon at 3:30. So those are my office hours and my email. And so in regards to course administration, let me start there. Here are the things you'll need. So you'll need a copy. You'll need Canvas, of course, and you must have got in through Canvas, I presume. And so we're going to use Canvas for posting lecture notes. We're going to post the homework there. We're going to post the quizzes and the tests there. We'll post solutions to homework and quizzes and tests there also. You'll need a copy of the textbook. So the textbook is College Physics by Vool and Surway, and the 11th edition is probably the most up-to-date edition. The 10th and the 9th editions also have the same content in them, although the section numbers are slightly different, and the problems that we do for the homework have different numbers. So it's most easy if you've got the 11th edition, but if you've also got a 10th or a 9th edition, I think that's fine too. And of course you could have a hard copy, a rental or a used copy or a new copy, or an electronic version of the textbook. For the weekly homework, we're going to use WebAssign for collecting the weekly homework and entering the weekly homework. So you also need a WebAssign registration. You can get your WebAssign access code with the purchase of the textbook, or you should be able to get your WebAssign registration separately without the access code or the bundle with the textbook. So either of those are fine. And if you go to WebAssign via the Canvas page, it should take you straight to our class. The tests that we'll take and the exams and quizzes, they're going to be administered through Canvas. They're going to be online and administered through Canvas and Zoom. I won't say too much about that right now. I'll talk about that a little bit more as we get close to a quiz or we get close to the tests and the exams. So this overhead is the things you need for the class. So this overhead shows you something about the structure of the class, how the class is arranged. This week is a little different than the normal week. So on this overhead, I've sort of imagined next week. So the homework will always be available on the Thursday morning of the preceding week. Then you'll have your Thursday morning lecture class where we introduce the material on the homework. You'll then have the following week's Tuesday lecture class where we'll further discuss the material that's covered on the homework. Then you'll have your Wednesday recitation class where you work through problems related to the homework. And then your WebAssign homework, that will be due that Thursday night. And so that's a sort of weekly sequence that will repeat over and over and again during the semester. You'll have 2 lectures, a Thursday and a Tuesday. You'll then have the Wednesday recitation. The homework will then be collected that Wednesday night. So this week, of course, we got recitations and lectures this week, and there are assignments posted for this week. But I would treat those as sort of practice for getting in the routine. They won't be graded, they won't become part of your grade, but it's important that you practice doing the WebAssign homework to check all that works for this week. You'll get some practice with the lecture quizzes and the recitation assignments this week. I can see a couple of questions about WebAssign problems. I've had maybe 10 or 12 emails about WebAssign problems. We've been slowly working through the WebAssign problems. So I see Ben, Isabella. I'll get back to you after the lecture class about your WebAssign problems. I know we've had things, and I see it in the chat now, related to the browser and other issues we're getting into WebAssign, but we have managed to fix them all so far, I think. Okay, so this slide shows you a portion of a table that's at the end of the syllabus. And it shows you sort of lecture by lecture the material that we're going to be covering. And let me see if I can, I'm failing to use annotate properly, and I want to clear that arrow. That's better. So lecture 1, as I said, the physics content that we're going to discuss is, the physics content is really dimensions of nature and units of measurement. So you see that there as a lecture 1 item, this guy here. And then you see the following lectures, lecture 2, 3, 4, and so on, as we work our way through August and September. And then you also see there our first test, which is in the middle of September. And so you could take a look at the full table at the end of the syllabus, and you can see the various topics that we're going to cover. And you'll also see in the table the over here the various section numbers of the textbook that we'll be covering as we work through the semester. Just a little bit about the course grading here. So the course grading will involve 2 tests during the semester and 1 final. And so you see that listed on the, oh, didn't mean to do that. You can see that listed here. These are the 2 tests and the final. There's going to be lecture quizzes, so they're listed here. And we'll probably do 1 or 2 lecture quizzes today if we get a chance, but we'll start lecture quizzes for credit next week. I mentioned that there's homework associated with the recitations. You'll hear about that in Wednesday's recitation class in a little bit more detail, but here's the assignment for the recitations. Then there's the WebAssign homework, and that's listed here. And then there's a lab grade, and that's listed here. So together, all those items will add up to 100% for your score. If overall you score 90% or above, then that's an A grade, 80% above, that's a B grade, and 70% above, that's a C grade. So that's how the different assignments, different grading is laid out. For the recitation, for the lectures here, one thing I'll do is instead of having excused absences, I'll drop your 4 lowest recitation scores. That way we don't have to keep track of a lot of absences, excused absences on individual quizzes, and we'll just drop your 4 lowest quiz scores. And then also on here for the final score, if the class completes the evaluation, the university class and instructor evaluation, then I'll also credit an extra 1% here. So that's how the grading will work. Okay, so I said that one of the things this class is about is understanding motion. And I pictured here on the left and the right. So over here on the left is some what we call celestial motion. And over here on the right, the basketball is an example of terrestrial motion. And so one of the things we're going to do, which was actually a huge breakthrough in science, is to uncover a unified description, explanation of all these types of motion. So of the celestial motion of, planets around the sun, to the sort of more everyday terrestrial motion of basketballs and footballs and so forth. So one goal is to get a unified description and a unified understanding of all those types of motion. You'll see that those different types of motion involve, for example, straight line motion, motion in a circle, motion in a curve that we call a parabola. And we'll be able to describe all those types of motion. And we're going to be describing them through some physical concepts. Famous one, is force. Another important one, I'm sure, is energy. But there's other concepts too, and they allow us to get a detailed, quantitative description of motion. So that's really one big goal for the course. In this slide, you see two of the sort of, I put celebrities here. So they're like the grandparents of understanding motion. So on the left-hand side is Galileo. So he was around, I guess, what is that? That's about sort of 400 years ago. And on the right-hand side, that's Newton, and he was around sort of 300 years ago. But anyway, these two guys put together the description of motion and the understanding of motion that we're going to try and uncover in these lecture classes. The other thing we're going to do is talk a little bit towards the end of the semester about the nature of material, the properties of matter. So that'll include, solids, liquids, and gases. And one of the reasons we're going to talk about the properties of matter is to illustrate, is an illustration of those concepts of force and energy and other quantities that we introduced in describing the motion of matter, in describing the motion of a basketball, describing the motion of the moon. So that's one reason that we look at properties of matter. We explore the properties of matter. And another reason is to get a glimpse, a sort of glimpse at the atomic, molecular, microscopic scale of matter. Okay, dimensions and units. So these are two topics, two related topics, but they're two distinct topics too, that we're going to talk about in today's class. It's going to be the entire content of today's class from now on. Okay, so the reason I'm going to talk about dimensions and the reason I'm going to talk about units is that we need dimensions, understanding of dimensions. We need an understanding of units before we move on to exploring the laws of nature, before we talk about forces of energy and other stuff. We need all those things. So specifically, I'm going to introduce the basic dimensions of nature in today's class. I'm going to talk about the technique of dimensional analysis in today's class. You'll find out what that is, why that's useful, how that's handy. I'm going to talk about units of physical quantities. And then we're going to talk about the procedures or the methods for converting units, which is also a useful, handy, important thing to be able to do. So these are the 4 items for today. Okay, so in this class, we're going to be concerned with, or thinking about 3 basic dimensions of nature. That's really all. There's mass or matter. That's one dimension of nature. There's space. That's a second dimension of nature. And then there's time. That's the third dimension of nature. And of course, I mean, you know already about mass and length and time. You knew that in preschool. And we're just going to expand on their meaning a little bit, their understanding a little bit in today's lecture class. Okay, so sometimes in lecture class, a little harder on Zoom, but I used to have celebrities come to lecture class, and I would have Lady Gaga come to lecture class when there's some really fundamental topics that we were talking about, and dimensions are a fundamental topic. And the way I think of dimensions is that, you know, if you're a home baker, then you work with flour and eggs and milk, and you use the flour, eggs, and milk to make all sorts of things. Well, the flour and the eggs and milk are the kind of the basic dimensions of home baking, like mass, space, and time are the basic dimensions of nature. Another example is that, you know, if you're an oil painter or whatever, watercolor painter, those primary colors, right? The red, the yellow, the blue, they are the basic dimensions that you work with when you paint, that you put together and produce all sorts of oil paintings or watercolor paintings. So those are another example that is like mass, length, and time are the basic physics dimensions. So that's one way of thinking about them. So I used to have Brad Pitt come to class too, and so here he is in our Zoom class. And the way he thinks about, for example, space and time, which is key to Physics 211, he thinks about them as kind of a, and I think this is a good way of thinking about them, as kind of a stage or an arena on which, for example, the the motion of matter plays out on that stage or that arena. The laws of physics play out on that stage or arena. We'll see how forces and energy and other quantities play out on that stage or that arena. One thing I've done on this slide is that I've used the shorthand. You'll notice it. I've denoted the dimension of mass by this uppercase M in square brackets, dimension of space by this uppercase L in square brackets, and this dimension of time by this uppercase T in square brackets. And so that's just the notation I'm going to be using. So it's an interesting question. It's also a kind of difficult question. If you ask, what actually are these basic dimensions? What are space, time, and matter? And I can tell you make a few statements, but I ultimately can't tell you exactly what they are. So we know that they were created in the Big Bang, and that was a long time ago, 15 billion years ago. It's hard to imagine that length of time ago. So they appeared, they were manifest in the Big Bang. As I say, actually, as Brad Pitt said, space and time are like this sort of framework or this scaffolding in which the motion of objects is played out, the laws of physics are played out, in which forces and energy are understood within this framework. But an interesting question and an unanswered question that you might wonder, and you might have wondered this in elementary school, or you might wonder it now, is why are there 3 space dimensions and 1 time dimension? And that just shows you that we don't understand everything about space and time, because we have no idea really why there are 3 space dimensions and 1 time dimension. So as you think about these basic dimensions, mass, space, and time, you want to be thinking them as the sort of basic building blocks of the physics world, as the stage on which things occur. But remember, we don't understand everything about them. There's lots of unanswered questions about them. Okay, so now I want to introduce a couple of terms or a couple of words. I've written the title of this slide as Irreducible dimensions and derived dimensions. It could have been irreducible quantities and derived quantities. So we think of mass, length, and time. We think of those quantities or of those dimensions as the most basic quantities or dimensions. And when we say they're the most basic, sort of fundamental dimensions, what we mean is we can't say that mass is built out of something else, some other dimensions are put together to make mass. Length isn't built out of something else, some other dimensions that are put together to make length. And time, likewise, isn't built out of something else that's put together to make time. There's no smaller bits or pieces that we can break mass, length, and time up into. So that's why they are basic dimensions. They're not constructed from more elementary dimensions or more elementary quantities. Then there's other quantities we call derived quantities. So, for example, here's a couple that I'm sure you're familiar with. Velocity is a derived quantity and sort of has derived dimensions. Acceleration is a derived quantity with derived dimensions. So you might know, and if you don't know, we're going to talk about it soon, that velocity, which measures how fast or slow we're going, is made out of the dimensions of length and dimensions of time. It's length over time. And you might know, and if you don't know, it doesn't matter because we're going to talk about it soon, that acceleration is made out of the basic dimensions of length and over time. It's actually length over time squared. It's acceleration's dimensions. And so velocity and acceleration are perhaps the most familiar, kind of most everyday quantities that are or don't have basic dimensions. They're not basic quantities. They're made out of the basic dimensions of length and time. Some combination of length and time. Some other famous examples that we'll talk about a lot in this class over the semester are force. Okay, so force is going to be really important in understanding the motion of matter through space and time. And force has rather complicated dimensions. I've indicated it on this slide here. It's mass times length divided by dimension of time squared. So force is a derived quantity. It's an important quantity, but it's a derived quantity. And it has a rather complicated set of dimensions in terms of the basic dimensions of mass, length, and time. But we'll get to meet force a lot throughout this class. So this little guy on the left here is going to be important to us. And then another one I wanted to mention over here, energy. Energy is also a derived quantity. Its dimensions involve the basic dimensions. So the dimensions of energy involve mass, length, dimensions of length, it's length squared, note here, and time, divided by time squared here. So again, like force, it's a rather complicated array of dimensions that are put together, packed together to form energy. But it too will be a really, really important quantity in understanding the motion of matter through space and time. And so this slide really just introduces you to the concept of, or the distinction between those irreducible dimensions of mass, length, and time, and the derived dimensions of things like, familiar things like velocity and acceleration, and maybe a little less familiar things like, but very important things like force and energy. Okay, so now I want to start talking about a very important technique, a very useful technique that's called dimensional analysis. And so I'm going to introduce on this slide, I'm going to introduce the ideas or concepts of dimensional analysis. And then we're going to look at illustrations or examples of dimensional analysis. So you're probably aware, and you're probably dreading the fact that in physics and in science, we use mathematical equations. And we use math equations for at least two things. I mentioned two things here. One thing we use mathematical equations for is to actually define new quantities. So, you know, we define the quantity of force through a mathematical equation. That's how we give rigor to its meaning. We define the quantity we call energy through a mathematical equation. We give rigor to its meaning by defining it through an equation. So that's one way we use equations. Another way is we use equations to express, to quantitatively express how things work. And when we write down an equation that expresses how things work, how this or that works, we're typically thinking of that as kind of a law of nature. It describes the behavior of nature. It describes how nature works. So it's a second way we use equations. An important feature about equations, whether they're defining a quantity in physics or they're a law of physics, is that the dimensions, we talked about these fundamental dimensions, mass, length, and time, the combination of dimensions on the left-hand side of the equal sign and the combination on the right-hand side have to be equal to one another. You have to, in a physics equation, have the dimensions equal on the left and right. No physics equation, this is an absolute rule. There is no exception to this. You can't have different dimensions on the left-hand side and the right-hand side of an equation. Oh, made a mess there. Okay. If you had different dimensions on the left-hand side and the right-hand side of a physics equation, it would be like, it's the physics equivalent of saying apples equals oranges, right? If you had an equation that said distance equals time, that doesn't make any sense, just like it doesn't make any sense to say an apple equals an orange. So any physics equation, any claimed physics equation that has different dimensions on the left-hand side or right-hand side must be nonsense. All valid physics equations have the same dimensions on the left-hand side and right-hand side. Okay, so now I want to, having introduced dimensional analysis, just show you a couple of little examples of dimension analysis. And I'm going to do these, go quickly through these two examples. So if I read question 1 here, it says, find the dimensions of linear momentum. So in this question, just imagine you've no idea what linear momentum is. And let's imagine that I've no idea either what linear momentum is. We're going to find the dimensions of linear momentum without knowing anything about linear momentum by the equation. It's a famous equation, but the equation we're told for linear momentum, which is that linear momentum is the product of mass and speed. So we're going to use dimensional analysis on that equation to find the dimensions of momentum. And then we're going to do a similar thing, question number 2 down here. It says, find the dimensions of kinetic energy. Again, I'm going to imagine that I have no clue what kinetic energy is. I'm going to imagine you've got no clue whatsoever what kinetic energy is. But we're going to find the dimensions of kinetic energy by dimensional analysis because we've been told an equation for kinetic energy. Here it is, that the kinetic energy is half the mass times the square of the speed. And using that equation and dimensional analysis, we're going to solve for the dimensions of kinetic energy. Okay, so let's do these 2 examples. Here's the first question. What's the dimensions of linear momentum P? So P is a symbol we always give linear momentum. You get used to that. Here's my solution, and let me just step through this solution for you. So the top line of the solution is my starting point. And it's what somebody told me or somebody told you, that you might not know what linear momentum is, but its definition is mass times velocity. So I wrote down the defining equation of linear momentum, the equation we use to introduce and define quantitatively linear momentum. So that was my starting point. Second step in my dimensional analysis was me thinking, well, I don't know the dimensions of momentum, but I do know the dimensions of mass and the dimensions of velocity. And so I'm just going to fill those in on the right-hand side. Dimensions of mass, well, that's a basic dimension. It's dimension I've written by the uppercase M in square brackets. Dimensions of velocity, that was a derived dimension, but it was a simple one. It was length over time, so I've filled that in too. And so here in that middle line is me filling in my knowledge, my understanding of the dimensions on the right-hand side of the equation. And then finally, that means that if the equation has the same dimensions on the left and right, the product of those dimensions on the right must be equal to the dimensions of momentum. And so we've found the dimensions of momentum. They're mass times length divided by time is this product of the dimensions of mass from the m in the defining equation and the dimensions of velocity from the length over time, the dimensions of velocity in the defining equation. I can see a few, let me try and get to a few chat questions here while I'm looking at it. Yeah, I will post the Zoom lectures, assuming I'm recording it, so fingers crossed. Are you posting a class notebook to OneNote? No, I put the class notebook in the course Canvas page so that you could use the notebook if you want to use it. But what I'm going to post are the Zoom lecture recordings and the PowerPoint, so the overhead slides. So you'll get those two things. You'll also see I'll post some demonstrations, little video demonstrations. I'll also post some work through problems. So you'll see those also. But I'm not going to do anything with the class notebook. But you can do stuff with the class notebook if you want to do stuff with the class notebook. Okay, Kaylee says, does velocity mean the same thing as speed without direction? Well, that's anticipating the next class. So next class, one of the things I'll talk about is velocity and speed. And I think you really got the right idea here. They are different, and they are different in a way in which velocity gives you information about the direction and speed doesn't give you that information. But I'm going to punt that to next class. Are lowercase m and uppercase m interchangeable? Okay, so that Olivia asked that. That's an interesting point. I used the lowercase m in this equation here. I use that lowercase m because that was a formula, and we normally write mass in a formula as typically we would write it as a lowercase m. The uppercase m here, I mean to specifically mean the dimension of mass. So one of them means a quantity of mass, the little m, and the big M, I'm specifically thinking about that dimension of nature I mean by mass. So I am distinguishing between the two of them in this solution. Joe asks, in this example, would we divide length by time first and then multiply by the mass, or some other way around? It does not matter. Okay, so whatever way you multiply and divide for the dimensions on the right-hand side, it's always going to be mass divided by time. Gerardo says, could a possible answer be that the dimensions of momentum be mass times length over time squared? Well, they can't be that based on the equation we were given. So the equation we were given was P equals mv. So I filled in the dimensions of m and I filled in the dimensions of v. If the equation that we've been given was P equals mv squared, which is incorrect, rather than the correct P equals mv, then the dimensions could be mass times length squared divided by time squared. Okay. Dimensions of kinetic energy was the second question. So let me just work through that. Kinetic energy, we tend to give the symbol K. And so we define kinetic energy, the quantity K, by this equation here, which we were given in question 2, that it's half the mass times the square of the speed. So the solution to the dimensions of kinetic energy, we're going to get the same way as we got the solution to the dimensions of momentum by using dimensional analysis. So you told me this. Whoever wrote this question on this slide, I don't know who he or she is, but they told me that the kinetic energy is 1/2 mv squared. So what I'm going to do, where I step in, is I start looking at the stuff on the right-hand side and filling in the dimensions of the quantities on the right-hand side. So the first quantity is actually a half. A half doesn't have dimensions. Half doesn't have dimensions of time or length or mass. So I indicated it's dimensionless with this dash in square brackets. It's void of dimensions. The mass, the little m, has dimensions of m, which I indicated by the uppercase M. The v has dimensions of length over time. So I put in the dimensions of v, but I had to remember it's squared in the equation. So we're going to pick up the dimensions of velocity squared when we think of the dimensions of kinetic energy. Anyway, at this point, I've shoved in all the dimensions on the right-hand side. And as we said, in any valid physics equation, the dimensions on the left and the dimensions on the right, the equal sign must be the same. And so the product of all these dimensions, which is mass times length squared divided by time squared, I've written it out here neatly, is the dimensions of kinetic energy. So that's another example of dimensional analysis. Okay, so this is going to be interesting. I wanted to try a quick lecture quiz to get practice with the lecture quizzes. Now, what I suspect is this is not going to be practice for you doing the lecture quiz. You'll know how to do the lecture quiz. This is going to be practice for me in doing the lecture quiz. And so I'm going to post a lecture quiz into our Canvas assignments now, if I can. This will take me a moment here. I've got to set the time that I'm going to make it due, I think. I'm not going to give you much time for these lecture quizzes. You're going to just look at them, think about them, and respond. I'm going to make this one due at 1:21. And I'm going to publish this if I can. So I'm thinking right now that, and this may be just my thoughts and not reality, but I'm hoping it's my thoughts and reality, that you can see a lecture quiz called Dimensions of Nature. And if you could go ahead and do that, then that'll be a practice lecture quiz. if you're having trouble opening the quiz, you could let me know through chat. This is going to be a practice quiz, and we'll get it sorted out afterwards. I do see some responses coming in. So some level, for some of you at least, it is working. And so we'll use this as a learning experience and see where we get. Okay, so I think that's the quiz. Let me say a few words about the quiz. So firstly, if you couldn't access the quiz or open the quiz or get to the quiz in time, don't worry for this particular class, this particular quiz, because nothing is counting this week. This is practice week. This is practice week for me. This is practice week for you. I did get some responses to the quizzes, but not a lot, which makes me think that, I've got to work something out on these quizzes. The correct answer from the dimensional analysis is that, so let me jump to the quiz here. Oh, no, actually, that's interesting. I was looking at the wrong quiz. So you're way ahead of me. That actually for this quiz, we got about 160 responses, which is good. And the correct answer is v squared. So if the equation for circular motion, the correct equation is going to be v squared over r. So v squared over r has the correct units to be equal to the units of acceleration. The other solutions do not have the correct units to be to have the right dimensions of acceleration. Okay, so that was a practice quiz, and we'll have another, for sure we'll have another practice quiz or two on Thursday's lecture class, as you and I both try and get used to this. Or maybe I try and get used to this. Okay, I want to look at another example of dimensional analysis. Second example of, actually a third example, because I already did two examples. I did kinetic energy and I did linear momentum. So this is a third example of dimensional analysis, a little more complicated example of dimensional analysis, but I think it's a really interesting example of dimensional analysis. It's kind of a cute example of dimensional analysis where you can learn some interesting physics just by thinking about dimensions of nature. So in this question, this problem, we're asked to imagine these two apples on the left-hand side. There's apple A over here, and there's apple B over here. And they're falling towards the ground. And we're told that in falling to the ground, apple B on the right travels twice the distance of apple A on the left. So B's going twice as far when it falls to the ground. A's only going half as far. And you're told also, I don't know who wrote this slide, but your instructor has lost his memory. And he can't remember the laws of physics. And we're going to try and work out how much longer it takes B to reach the ground compared to A, given that it's falling twice as far to get to the ground as A. Okay, so let's start our solution here. And on this slide, what I'm going to do is just think about, before I apply actually dimensional analysis, I'm going to think about what things could the time to fall to the ground depend on. I mean, could it depend on the color of the apple? Probably not. Could it depend on whether it's cloudy or not? Probably not. But I'm going to think of some things that it could depend on. So it seems to me that it's plausible that the time to get to the ground for apple A and B could depend on the distance to the ground. So that's one obvious thing. And I think we'd all guess that. Also seems that maybe it could depend on the mass of the apple. You know, whether the apple is light or heavy could affect the time it takes to get to the ground. So let's write that down too. And then finally I said, well, look, apples only fall to ground because of gravity's pull. Without gravity's pull, apples wouldn't fall to ground. If you went into outer space, apples don't fall to ground. And so given that, let's assume that the apple's fall to ground could depend on gravity. So now I'm going to start with the fact that I've come up with this hypothesis that the fall to ground could depend on all these things. Let's try and see if we can solve this problem. So upstairs here is going to be, on this slide, is my starting point. This T here is the time to fall to ground. And the M, the Y, the G are the mass of the apple, the distance it falls, and the acceleration of gravity. These are the things that I said that the fall to ground could depend on. And I'm going to use dimensional analysis. I'm going to use dimensional analysis to step from this hypothesis to a solution to how the apple depends on those three things, which is down here. And so I want to explain this little path from upstairs here to downstairs here. Now I got a little technical problem here in that I've completely lost here, I'm back. I couldn't see my chat anymore. And that's making me very nervous. I thought I was now completely talking. The only way I know I'm talking to you, right, is that I see some questions. And if I didn't see the questions, then I'm starting to think, well, maybe I'm not connected to the internet anymore or something like that. But anyway, I see the questions again now. Okay, so how did I get from upstairs here, and a hypothesis that the time taken depends on mass and distance and acceleration of gravity, to this little formula down here? That is how exactly the time depends on or is proportional to the distance and the acceleration of gravity. Let me show you how to do that. So the hypothesis was that it depended on these three quantities, but I don't know whether it depends on mass, mass squared, mass cubed, 1/mass. So that uncertainty about the power of mass, I just wrote as this power A. I don't know what power of mass it is. And the same things for the distance and the acceleration of gravity. I'm guessing it depends on the distance it falls, but I don't know how it depends on the distance it falls. So B expresses that unknown. I'm guessing it depends on the acceleration of gravity, but I don't know how it depends on the acceleration of gravity. So C expresses that unknown. Okay, so then I started filling in the dimensions of these four quantities. On the left, it's easy, right? That's time. on the right-hand side, I've got to fill in the dimensions of mass, uppercase M, length, distance, uppercase L, and acceleration of gravity. That's an acceleration. Its dimensions are length divided by time squared. I filled all those three things in. And you notice the little a, the little b, the little c. Those are those unknown powers, and I've got to figure those out. So how am I going to figure those out? Well, I did them one at a time, step by step. Let me explain how I did that. Since the dimensions must be the same on the left-hand side as on the right-hand side, then it means that the right-hand side here must have the dimensions simply of time, because the left-hand side simply has the dimensions of time. Well, this mass then, what must be the power on this mass to make it vanish, to make this dimension vanish? The only solution that makes this dimension of mass vanish so the left-hand and right-hand dimensions can be the same is if that power is zero. And so I looked at this dimension of mass on the right. I said it must vanish over here on the left. And so that told me that A equals 0. I next did a similar thing for time. I said I've got to get time, dimensions of time, over here on the left-hand side. So how must it be that I get dimensions of time out of this expression here? Well, there's no time in the length, but there is a time in acceleration. And acceleration has the dimensions of 1 over time squared. So to make that 1 over time squared into a dimension of time, I've got to A, take the square root of it to turn the time squared into time, and then I've got to take 1 over it to take the 1 over time into time. And so that told me that the dimensions, this power C, that must be -1/2. T to the power -2 to the power -1/2. Multiply these two powers, you get 1. That's how you get the dimensions of time over here. And so that told me that this power C is going to be this -1/2. And then finally, I just had to do the same thing for length. This product of this length here to the power B and this length, which is to the power -1/2, must cause the length to vanish, because we only have time on the left-hand side. And so it has to be that B is a half, because then length to the half times length to the -1/2 causes the length to vanish. Causes the to the length to vanish. Yeah. So we end up with determining the three values of the three powers, A, B, and C. A was 0, so there's no dependence on mass. That was my conclusion down here. B is a half, so it depends on the square root of the distance fallen. That's my conclusion here. And then C is -1/2. So it depends on the -1/2 power of the acceleration of gravity. And that's what's expressed here. And so that's a really, really powerful example, a really, really important example of dimensional analysis. And we've used it to figure out that the time taken to fall a certain distance goes as the square root of the distance, which means, supposing we call the distance that the apple A fell is y, then if apple B falls twice as far, 2y, then because the time is proportional to the square root of y, the time is the square root of 2 times as long. So 1.41 times as long. Okay, let me take a look at I think there was a question on this. How do you know when to use acceleration and when to use velocity? We'll talk about that let me punt that question too to the next class, because next class will all be all about the distinctions between acceleration and velocity and other examples. So, velocity tells you how fast or slow you're going. Acceleration tells you whether you're speeding up or slowing down. But we're going to really talk about that next class. So we'll get to answer that next class. Okay. Let me skip that, and get on to the last topic for today's class. And that's the units of different quantities. So we use units. You and I use units. You've used units since you're in, kindergarten to measure quantities. So some everyday examples of units are the fact that, you buy eggs in dozens. A dozen is a unit, means 12 eggs. If you're getting a diamond ring, right, you weigh diamonds in a unit called carats. So that's another example of a unit of a unit of a quantity. And if you were to measure, if you go out on your boat and you want to measure the depth of the ocean, then typically depths of oceans are measured in a unit we call the fathom. And these old-fashioned units, a lot of things like lengths and masses and things like that were based on dimensions of the human body, right? The fathom is actually the height of some average human. And so that's how the fathom came about. And they were just convenient units for the things that were going on when you were a pirate, or you were a farmer, or you were a whatever, 500 years ago. In science, all right, I'm not a pirate and I'm not a farmer. In science, we tend to use scientific units. And the scientific units that we most often use are called the System International units, SI units, or they're sometimes called just the metric units. So for mass, we use the kilogram as a unit for measuring mass. For length, we use a meter as a unit for measuring length. Time, we use a second for the unit of measuring time. And obviously you're familiar with kilograms, meters, and seconds. How could you not be and be 20 years old? I'm familiar with them. I was familiar with them when I was 20 even. So they're convenient. These kilograms, meters, and seconds are pretty convenient for everyday life, our everyday world. So we often use these units. Just to make this last point here, so us humans have invented units. We invented a kilogram and a meter and a second. Nature, on the other hand, nature was responsible for inventing, not right word, but inventing mass, length, and time, the basic dimensions. The next 3 slides, I'm gonna shoot through really quickly because that's all I need to do with them. This is a table from the textbook. It just shows you the huge scale of lengths that you can meet in physics and astrophysics. So it shows you that the largest distance scales can be like 10 to the 28 meters. The smallest distance scales can be 10 to the minus 15 meters. It's from the size of a single proton to kind of the size of the universe, or a distant object in the universe. So there's huge ranges in physics of distances, from very large powers to very small powers when measured in meters. And the same is true of time intervals. There's big times like the age of the universe. There's tiny times like the time it takes light to cross a proton. And there's also huge ranges of masses, from the mass of the universe, it's some huge number, in kilograms to the mass of an electron. It's a tiny number in kilograms. Look here, I don't remember the mass of the universe, but apparently the mass of the universe is about 10 to the 52 kilograms. That's enormous. It's unimaginable. The mass of a proton, I do remember the mass of a proton, is about 10 to the minus 30 kilograms. It's some tiny, 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 I can't see tiny enough, fraction of a kilogram. But anyway, that just gives you, indication or appreciation of the huge scale of different masses, of different times, of different lengths in physics. One thing that we often have to do is convert units, unfortunately. For example, especially in the US, we're we're sort of essentially the only modern country that still uses imperial units in things. And so often we have to convert between imperial units and scientific units. So imperial units are this sort of really bad hangover from the British Empire. And imperial units are things like the mile, the 1,609 meters in a mile. They're things like the inch, right? There's 2.54 centimeters an inch. None of those things are overly interesting, but we do have to work with imperial units and scientific units in science and engineering and medicine, because we've inherited, imperial units and scientific units. There is a famous example of not converting units. I'll just mention it. And that is the loss of a spacecraft called the Mars Orbiter, which took nearly a year to travel from Earth to Mars. It took, thousands of person years of effort in building the spacecraft, flying the spacecraft on its way to Mars. And it was lost when it got to Mars. It crashed into like a Mars hillside or a red Mars dune, sand dune, because of forgetting to convert units. There was an engineering team, there was a science team, they exchanged information, and one used imperial units and one used scientific units, and that's how they lost the Mars orbiter. So it's like a really, really sad story, and says that converting units is not just irritating, but it can be really important. Okay, I'm going to do one last calculation in the last 2 minutes of this class. And what I'm going to do in these two examples of converting units is to show you the conversion of units for question number 1. We're told that the speed of light is 3 times 10 to the 8 meters per second. So that's the speed of light from, flashlight or whatever source of light, sunlight, in meters per second, scientific units. We're going to convert it into miles per hour. Miles per hour is important in our everyday life. We drive a car and we want to know the miles per hour because we don't want to exceed, the speed limit, but we want to, not exceed the speed limit plus 10% or whatever, however we drive. Okay, so let's do this first question. Calculate the speed of light in miles per hour. So I've written down here the speed of light in meters per second. It's 300 million meters per second, 3 times 10 to the 8 meters per second. Then I'm going to multiply it by 2 conversion factors. One is to convert the units of length in the speed, and the other one is to convert the units of time in the speed. So over here on the left is the conversion for the length, the meters in the velocity. And over here on the right is the conversion for the seconds in the velocity. And these factors will convert us from meters per second to miles per hour. And the way they work is for the conversion of the lengths, we're going to multiply by this quantity in parentheses. Is 1 mile over 1,609 meters. Numerically, that's 1. because 1 mile is 1,609 meters. But what it will do is cancel out the meters in the units and replace it with miles. Likewise, over here on the right, this factor here, 3,600 seconds over 1 hour. I happen to remember that there are 3,600 seconds in 1 hour. So that quantity is also 1 unity. And so it won't change the speed, but it will cancel out the seconds in the denominator here and replace it with hours. So let's see how that works. First, I canceled out the units. So the meters upstairs cancel with the meters downstairs. The second downstairs cancels with the second upstairs. That leaves me with just units of miles per hour. And then I multiplied 300 million by 3,600 and divided by 1,609. And when I did that, I got this number. This huge number, nearly 700 million, 670 million, is the number of miles per hour that light travels at. And so that is the speed of light in miles per hour. And so that's an example of converting units. Okay, well, that's the end of today's class. I'm going to stay on for 10 minutes after the class or so, or however long we need. And I'll try and answer some of your chat questions or other questions you have in that period. Today's class, we basically covered dimensions of nature and the units that we measure quantities in. And those are going to be a foundation that we're going to use in the upcoming classes, starting on Thursday's class, for exploring motion of matter through space and time